Hello, this is the chemistry and biology of cocaine, a video presentation, a crack at cocaine, if you will. So, what is cocaine? Cocaine is a powerfully addictive stimulant drug made from coca leaves native to the continent of South America. Its known effects include leading to extreme happiness, sexual arousal, sweating, dilated pupils, and high heart rate. As a street drug, its appearance is a fine white powder. Popular names for it include crack, coke, snow, or blow. The name crack comes from the cracking or popping noise that the baking soda makes when it's heated up, both during manufacturing and when it is smoked. The two most common ways of using cocaine powder is to snort it through your nose or rub it into your gums. Cocaine is frequently illegally abused and is actually second most frequently abused drug, behind cannabis. I've previously mentioned the name crack, but what is the difference between crack cocaine and traditional cocaine, if there even is a difference? Well, traditional cocaine is a salt, while crack cocaine is molecular in structure. Both the ionic salt and molecular form of cocaine are involved in cocaine processing. Cocaine hydrochloride salt, traditional cocaine, is what is commonly sold as cocaine powder. It is traditionally to be injected or snorted. If the cocaine hydrochloride salt is treated with alkali, it becomes the neutral molecular base. This alkali is often baking soda. It is used to make crack, one form of free cocaine. If the hydrochloride salt, traditional cocaine, is smoked, heating it up destroys most of the cocaine, whereas the molecular base, crack form, is more volatile. So more cocaine molecules can survive and be absorbed. Crack cocaine has a simple molecular structure, so it has a lower boiling point. So let's move on to some chemistry, the synthesis of cocaine. The synthesis of cocaine involves many steps where cocaine is converted from its ionic form to the molecular form and vice versa. Many steps are focused on purifying the cocaine. Firstly, we must identify neutral cocaine molecules from coca leaves. We often use a weak base, lime. Second, kerosene is used to extract cocaine from the leaf, and sulfuric acid is added to the kerosene. The cocaine is protonated, as we can see in the diagram below. It gains an H+ ion and forms cocaine sulfate. Next, we add an alkali like lime to precipitate neutral cocaine molecules, creating a crude coca paste. The purity of this crude coca paste is variable, so cocaine synthesis is a very unreliable and difficult process. Next, the crude coca paste is shipped to a lab, where impurities are removed by adding sulfuric acid and potassium permanganate, a common oxidizing agent, to oxidize the impurities. As an acid was added, sulfuric acid, cocaine becomes protonated again and requires adding ammonia to neutralize the cocaine sulfate. After filtering off insoluble impurities, hydrochloric acid and propanone, a ketone, is added to give cocaine hydrochloride, are also known as traditional cocaine, as we've previously mentioned. So, how does cocaine produce its effect that gives extreme happiness? You've probably heard of the chemical dopamine. Dopamine is one of the neurotransmitters in our body in charge of making us feel pleasure. Normally, dopamine is released by a neuron, and it binds to dopamine receptors on dendrons of adjacent or nearby neurons. Dopamine is later recycled via dopamine transporters. The molecule dopamine transporter is really important in explaining why cocaine produces its effects. When cocaine molecules are present, they bind to these specialized dopamine transporters and disrupts the recycling of dopamine. The result? A buildup of dopamine in the synapse, which causes short-term but extreme happiness. How does cocaine affect the brain? Cocaine has a huge impact on the limbic system, the part of the brain responsible for emotions, behaviors, and long-term memories. The other parts of the brain are the neocortex, responsible for rational and thinking, and the reptilian brain for instinctual, or also known as the dinosaur brain. The nucleus accumbens of the limbic system has a high concentration of dopamine responsive cells that produce feelings of pleasure when stimulated by dopamine, so it is particularly affected by cocaine. The nucleus accumbens plays an important role in the reward circuit as dopamine promotes a desire to do something. The limbic system contains the hippocampus, a memory center, which helps cocaine takers remember what action taking cocaine led to extreme dopamine release in the nucleus accumbens. It even imprints people, places, objects related to taking the drug, leading to a high chance of relapsing and retaking the drug. Studies show that chronic cocaine exposure can cause increased branching in the dendrites of nerve cells in the nucleus accumbens, causing these neurons to receive more signals, meaning other regions of the brain have increased influence over the nucleus accumbens. For example, memory centers have enhanced outputs to the nucleus accumbens due to the increased branching in the dendrites, causing intense craving of cocaine, as the memory center has imprinted cocaine-related memories to intense happiness when cocaine-related memories occur. This is why cocaine is so addictive, as frequent takers may maybe see a tool that they use to abuse cocaine with, and that leads to an intense want of abusing cocaine. It affects the nucleus accumbens, which is involved in the reward circuit. The image on the right shows the glucose metabolism in the brain of a cocaine-addicted subject. As you can see, this indicates reduced activity in the orbitofrontal cortex in the cocaine-addicted subject when compared to a non-cocaine addicted subject. The OFC, the orbitofrontal cortex of the brain, is involved with cognitive thinking or decision-making. Problems with it are linked to many mental or behavioral issues, such as addiction, bipolar disorder, or PTSD. By diminishing OFC functioning, cocaine usage can lead to poor decision-making. So, not only does the intense craving of the highly addictive cocaine affect our decision-making, it is also because it affects the orbitofrontal cortex of the brain. Experts suggest strengthening OFC activity, e.g., following a proper sleeping schedule, as a possible therapeutic way to make addicts be more aware of the harmful effects of cocaine. Alcohol and cocaine are often taken together, as cocaine abusers believe that alcohol acts as a depressant, so it counteracts the happiness effects caused by cocaine. The left route is how cocaine is metabolized in the liver with the help of the enzyme HCE1 carboxyl esterase, which catalyzes the hydrolysis of cocaine into benzoylecgonine, which can be detected in cocaine users' sweat, so it can be used as a detector in testing for cocaine usage. If ethanol is present during the metabolism of cocaine, it takes a different route. A portion of the cocaine undergoes transesterification with ethanol. So instead of undergoing hydrolysis with water, which is shown on the previous slide, of normal metabolism, which results in the production of cocaethylene, a substance that binds more tightly to dopamine transporters and is 30% more toxic than cocaine. Alcohol also slows down metabolism in the liver, causing more cocaethylene to remain in the body, and it can pass through the bloodstream and can cause harm to other tissues and organs. This is why taking cocaine and alcohol at the same time is extremely dangerous and can often be considered lethal. Cocaine addicts can often be pictured with nose injuries or maybe nose bandages over their nose. This is because cocaine actually affects the nose in multiple ways. One of the most common is cocaine nosebleeds, a common side effect of constant cocaine usage. When cocaine comes into contact with the inner part of the nose, it can lead to decaying cartilage and the skin of that part of the nose, leading to a higher chance of nosebleeds. Another side effect to the nose is a cocaine nose collapse. Cocaine constricts blood vessels and limits the blood flow to the septum, so less oxygen is delivered to the septum, which can then cause the cartilage to die and holes to form. A cocaine nose collapse can occur since the septum cartilage is what supports a person's nose. So that is all I have to say on the biology and chemistry of cocaine. I hope you enjoyed it and learned a lot.